right, as we start chapter 6, I want to let you know that we're covering very briefly 6.1, 6.2, and 6.3. I'm essentially treating that as one big section, although I'm going to create 3 separate playlists, one for 6.1, one for 6.2, and one for 6.3. But I'm treating that as one big section, and if you look, I think I assigned about 5 homework problems for each section, so it's a total of 15, okay? So when you see that we're covering those 3 sections plus something from chapter 7 in 1 week, don't freak out. It really is, we're just taking a very quick look at reviewing the notion of solving triangles that we can do. So in 6.1, we're going to be working specifically with right triangles, and then in 6.2 and 6.3, we'll be using the laws of sines and the law of cosines to solve oblique triangles, which is just a triangle that's not a right triangle. Okay, so I want to just remind you of a naming convention that we have for triangles. If I name the 3 angles with the capital letters A, B, and C, then I can name the 3 sides with the lowercase letters A, B, and C. And the convention is whatever side is opposite angle A, we call side A. Whatever side is opposite angle B, we call side B. And whatever side was opposite angle C, we call side C. Generally speaking, if I have a right triangle and I'm naming them A, B, and C, we're going to call the right angle C. There's no rule that we have to, but we usually do, and I will for this section. That's the convention established in the book. This convention of naming the sides by the angle that they're opposite works, even if it's not a right angle. So when we're working with oblique triangles in the next couple of sections, capital C isn't going to necessarily be a right angle anymore, but side C will still be the side that is opposite that angle. Okay, so then I also tell you that to solve a triangle simply means to give the measure of all 3 sides and all 3 angles. So it's giving a total of 6 pieces of information. And generally, if we have 3 of those pieces, as long as it's not all 3 angles, we have 3 pieces of information and at least one of those pieces is a side length, we generally have enough information to solve the triangle. Having all 3 angles would give us the shape of the triangle, but I could have any size. It would give me the correct proportions or the ratios between the sides, but it wouldn't tell me how big the triangle was. We've seen that we can have a 30, 60, 90 triangle of any size that we want to, but the ratio between the sides is always the same. Okay, so I've got an example up here. This is a right triangle. This picture applies. Now this picture is not necessarily drawn to scale, but we're told we've got a right triangle where angle A is 20 degrees and side B is 3.5 centimeters. Okay. So I could draw myself a picture. Now I could go with that picture if I wanted to. I might actually prefer to draw something that's a little bit nicer looking. That looks a little closer to 20 degrees to me than it did a moment ago, but it doesn't really matter. It doesn't have to be a picture that's to scale. Side B was 3.5, so I'm going to need to know the other 2 sides. So I'm going to need to know side A, I'm going to need to know side A and side C, and it looks like I'm going to need to know angle B. So let's just write out what we do have. We've got angles A, B, and C. A we were given is 20 degrees. C we were given is 90 degrees. Now I can get angle B pretty quickly because the angles in a triangle have to add up to 180 degrees. So that's going to make B 70 degrees. Excellent. So then I need to get these 2 side lengths. Okay. And I like to, when I can, use the given information rather than anything I've calculated. Now I feel pretty confident that I got the 70 degrees here right, but I'm going to just play it safe. I'm going to go with the 20 degrees in case I'm having one of those brain farty sort of days, and that's actually the wrong thing. So let's say I wanted to find side A. Well, I know angle A, and A would be opposite it, and I know the adjacent side. So I can just say tangent of 20 degrees would equal A over 3.5. Now that means that A is going to be 3.5 times tangent of 20 degrees. Now, that's as far as I can get without the aid of technology. So at this point, I'm going to do something that I very rarely do. I'm going to pull out a calculator. Okay. Now, if I'm testing you on this, this would be a great thing on a take-home quiz, because on a take-home quiz, you're allowed to use a calculator. And I would simply tell you what place to round things to. In this case, let's round everything to the tenths place. In a lot of applications in science classes, you're often working with rounding to significant digits. And in our trig class, if you took that here, like last semester, I was teaching significant digits then. Our book doesn't address that, so I'm not going to add that to the book. Okay, so I am going to say 3.5 times, actually what I'm going to do first is I'm going to check the mode of things and make sure that I'm in degree mode, because if I'm in radian mode, that's going to be a problem. Okay, what I just did, there's usually on most calculators there will be a little D or an R to tell you whether it's in degree or radian mode. It's hard for me to read that. So what I just typed in is sine 90, and I got 1. I'm in degrees, because sine of 90 degrees is 1, but 90 radians is not coterminal with 90 degrees. So if I were in radian mode, that would have given me something other than 1. It's a nice quick way to check. Okay, so I'm in degree mode, so I'm going to hit 3.5 times tangent of 20, and I'm getting 1.273 blah, blah, blah. I said we were going to round to the tenths place, so that would be approximately 1.3. So A is about 1.3. Let's go ahead and include units, that's centimeters. Generally, if you're rounding, I recommend this, that you write down a digit or two past what you're rounding to, and that way, if you were to write that you got this, but you rounded it to 1.2, I know where you made your mistake. You did the problem right until the last step of rounding, and that helps me in assigning partial credit. Okay. All right, excellent. B was given. B was 3.5 centimeters, so now I just need to find C. Now, I've got a couple of options. A lot of times once people have two sides, they want to use the Pythagorean theorem. And that's actually what your book does in a similar example. It would be better, however, to just use the given information. If I'm using the Pythagorean theorem, and I've just said this is 1.3 centimeters, I've just rounded that. And so I'm less confident of that than I am of this given information. Now, one way I could get around that is I still have the 1.273895 blah, blah, blah in my calculator. So I could go with that, which would be a little bit more exact. But what I'm going to do instead is I'm going to just use the given information. I'm going to say this was given and this was given, and I want to know C. I'm thinking let's use cosine. So I can say cosine of 20 degrees would be 3.5 over C. Now, if I want to solve for C, let's multiply to get it out of the denominator. So C times cosine of 20 degrees is 3.5. C would be 3.5 divided by cosine of 20 degrees. Okay, so 3.5 divided by cosine of 20 degrees, and I'm getting 3.72. 724, blah, blah, blah. If I'm rounding to that place, that's going to be about 3.7. And I can do a quick check. C is the biggest side. C was the hypotenuse. It should be longer than either of the other two sides. Okay. Now, I mentioned that it's best, if possible, to use the given information rather than use values that you've just calculated. I do think that's important, but we're covering this section fairly quickly, and the book sets a bad example because they actually go ahead and in a similar problem, they go ahead and do the Pythagorean theorem. So I'm going to mention that it's always best to use the given information if possible. I'm going to encourage you to do that because you may encounter in classes in the future that that is required. But I won't penalize you if you show your work and you use calculated values rather than given values, simply because the textbook sets a bad example, and I don't want to slow us down too much by saying, okay, ignore this part, but read that part. So there we have it. I will tell you one thing that you are not responsible in section 6.1 is bearings. Bearings is a really neat application of trig. Bearings is how we take measurements with the compass, and it's fairly interesting, I think, and it's something that was covered in trig. So you're certainly welcome to read through those examples, but I'm not going to hold you responsible on that particular application this semester.